In the previous video, we talked about the choose double slit experiment and the wave model, and we introduced what happens when we start considering photons instead of waves. And today, in this video, we will discuss the concept of state. So, what is a state? In general, the state of a system is the maximal information we can have on this system. So, for example, for the photon passing through a slit, okay, imagine a plate with two slits. Now we close this slit, and only the first slit is open. So the state of the photon passing through the slits is described like this. So, okay, this collects all the information on the wave that arrives here on the plate. Okay, so this collects all the informations about the photon. As the same, if we close the first slit and not the second, we have this state. Okay, so, but there is more. The presence of these two, we can say, mutually exclusive classical states, so implies the presence of this third state. And the interpretation is of this state is highly non-classical, because this actually means the state passed through both slits. But yeah, we know that it's not possible. So how can we explain this? We know it's not possible for the photons to pass through both slits, because in the original double slit experiment there were several attempts using detectors. So using detectors, you can actually know if this is D1 and imagine another detector D2. They can measure if the photon is passing through the slits or the slits, and the detector always detect only one photons, or here or here. It's not possible for the photon to pass through both slits at the same time. So now let's move further, and for example, we will now try to introduce a damper in the first slit. What is a damper? So it's something that destroys part of the original ray that arrives in the first slit. Okay, so we're talking about photons, so something that destroys, did not let some photon pass, so it's a damp coefficient. So some photons are destroyed by this damper. Okay, imagine this here. So we have a damper here. This can be represented by a photomultiplier. So, for example, how can we describe the electric field in this case? We introduce a damping coefficient here. Okay, now we can calculate the intensity. So the intensity will be it's not difficult to prove. And as you can see, this must be greater or equal than okay, because this is the of this cosine, so this value, so this must be greater than this term, and this is equal to tau minus 1 squared, which is greater than 0. So what we can say about that, we get equal to, okay, greater or equal than 0. This means that we no longer have dark spots or dark parts on our plate. So this is important to notice. But also, what we get is that the contrast, okay, we denote this letter, the contrast is this one. Is less than 1, so we have less contrast than in the previous case where there was not the damper. Okay, but also that this one is the maximum intensity, so okay, the maximum intensity obviously will be when this term is equal to 1, so Emax, Imax will be tau equal to, okay, but this is less than 4, okay. So the maximum intensity is less than the previous case, and the contrast is less. Okay, now we can try another modification. Alright, I'll get a new page. Okay, now imagine to introduce a glass that can shift the phase of the ray. Okay, so imagine a glass. So for example, we put glass only in the second slit. Sorry. So how we can calculate the intensity in this case? It's easy. So okay, this factor is due to the phase shift introduced by the glass. So causing the okay, the result would be a shift of the point where the photon converges along the y-axis. So this is y-axis. So we'll get, okay, this point. Okay, this point will be shifted by this term. Okay, and of course the maximum of intensity will be centered in. It's easy to see that. Okay. Okay, so in this scenario, the state will be described as follows. So and okay, so more generally, we can write our state in general like this. Okay, we constructed a state. This is a state space, okay, constructed with 4 parameters. Okay, the important thing to notice is that we actually asked 2 questions to our experiment. The first question is, in which point of the plate the photon arrives? Okay, and the second question that we ask our experiment is, through which slit the photon pass. So where it arrives and through which slit the photon passes actually. So the question is that these two questions influence dramatically each other. So if you answer the second question by introducing a mirror, you change the result of the first question. Okay, so they are not independent. Okay, now okay, another example, if then we measure where the photon pass, we know that we lost interference, okay? When you measure one outcome, you always get this outcome. So you, by answering the second question, you lost interference. So there's these 2 questions are closely influenced by each other. So. Okay, let's consider the first case now. The first case was the case where there are no damping coefficient or mirrors. So, the probability for the photon to pass through the first slit or the second slits are the same in this case. So, P, we can say that P1 equals to P2. So, second case, the case of the damper. Okay, we say that the intensity, okay, the state in general is the damper is on the first slit, so okay, the intensity will be so. If we said in the previous video that intensity and probability are linked together because like intensity can be viewed like the number of photons yeah, like a number of photons. So number of photons is correlated with probability. So okay, the intensity with only the first slit will be this one, and with only the second slit will be this one, okay, without the interference term given by this guy. So ES1 only. We are in this section. I will try to be clear. We will try to derive the probability for the photons to pass through slits 1 or slit 2 and compare those probabilities. So here we get, okay, so we can say that the probability of the photon to pass in the first slit divided by the probability of the photons to pass in the second slit is tau squared. So can relate, all right. But we also know that the probability must add up to 1. So easy math here. And you can easily see that this is just algebra. I will not talk much about that. So, okay, these are the probability for the photon to pass through the second and the first slit. Okay, now let's consider the third case. Okay, the state was described by this guy. And in this case, no photons is stopped by this mirror, by the mirror. No photon is stopped by a mirror. So this term doesn't really influence the probability. So we always have in the fourth case, the most general one. Okay. Okay, so I will try to be more clear. No photon is stopped by the mirror, so the mirror doesn't influence the second question, the question through which slit the photon pass. Okay. But will be important in the first question, so in the interference. Okay. So introducing a phase shift will have an effect on interference, but not on the probability of the photon to pass through one or the other slit. So in this third case, we simply have this one. Okay, now we'll open a new page. We said that we were asking two questions to our experiment. The first one was in which point of the plate the photon arrive, and the second was which slit the photon, through which slit the photon pass. So we know that I'm telling you that imagine to have a detector, D1 and D2, and having the photon in a state like this. Okay, if you are detecting using detectors to measure where the photon is passing, and imagine to get like the D1, the photons is passing through this slit, okay, then you will always get one. Okay, this is called collapse. So the answer to the question 2 is totally random. Okay, the answer to the question where is the photon passing is totally random, and there is no official interpretation for this.